Okay, so the first memory that we're going to deal with is our magic little array of these 32 scratch pad registers. They're placed where almost all the instructions get their operands and write their results. So we actually have this little group of 32 registers. Each one of these little rectangular boxes is a 32-bit register, can hold 32 bits of information. So these heavy lines here are actually 32 signal wires all coming in this case, to this particular register. We supply two addresses, if you want to call them that, or select lines, one of which will select information from any one of the 32 registers and provide it, give that value, that 32-bit value, on the read port down here, the A port. And again, we have a different set of address wires that independently selects any one of the 32-bit values to the second read port. So the two read ports are completely independent. They could read the same register, they can read different registers, depending on what the A cell and B cell signals are. How many bits wide is the A cell signal? It has to select one of 32 registers, so how many bits should we be sending in? We should be sending in 5 bits, right? Because it takes 2 to the 5th. With 5 bits, we can specify the 32 possible combinations of addresses that would let us select which one of the 32 registers we're reading. There's also a 5-bit destination number that is used. This is a decoder here. So given a 5-bit number here, only one of the 32 output lines will be on, and it controls which one of the registers will be written at the next rising edge of the clock. And just to remind ourselves, a clock-enabled register, that's what this little EN is supposed to signify, the enable signal. When the enable signal is high, the register will be loaded with whatever's coming in on the D wires. And if the enable signal is low, the register is loaded simply with its old value. So you can say, well, why don't we just do something fancy with a clock, do some logic so that the rising clock edge doesn't happen. And that turns out to be fraught with danger as you get down to low-level circuit design. And it turns out that this little diagram here, which involves this little 1-bit multiplexer, is a much safer way of implementing clock-enabled registers. And so almost all designs that I know of do that. The trouble with using logic to do clock gating is that any sort of little glitch in the logic will might produce an accidental clock edge, and the register might clock accidentally. As you change the values on the enable signal, you don't want all of a sudden a clock edge to be produced. And so this way, the clock goes directly to the registers, and we're using the enable signal to control what the registers will load. We're going to package this up into a single module, which we call a 3-port register file. So the register file is the name for this little 32-bit scratch pad memory that has 32 entries in it. So we send in 2 5-bit read addresses, and some amount of time later, it's what's called a combinational read port. No clocks involved. TPD, after the addresses become stable, we get the information out of the register file down here on the RD1 port and the RD2 port. So we're reading 2 separate registers out into the 2 data ports here. And then we can also supply a write address and some write data, and a signal that, by the way, says, I want you to write. So if we don't want to write at all, we can turn off that write signal. We can use the write enable to say, ignore the write address and the write data, don't do any writes at all. So that's sort of like another control signal that says that 32-to-1 decoder that we had, or the 5-to-32 decoder we had that selected which enable signal to produce, to enable to write into the register, to pick a register to write into, we can just disable that logic altogether. I'll say more about that in a second too. And then the write happens at the rising edge of the clock. So this is really just like a register. The writes happen at the rising edge of the clock. Which register gets changed, if any, is determined by the address wires and the enable wires. And what the new data will be is determined by the write data wires. Here's a timing diagram of how the register file works. And these are the sort of things you see in data sheets all the time when you buy digital components. These are the sort of timing diagrams that you have to sort of learn to read. What this one is telling me is that a certain length of time, so this number is in the case of our beta, about a couple nanoseconds. After we have a stable read address, we will get the appropriate data out of the register file. On your machines that are sitting in front of you, that number is more like, tens of picoseconds. So it's the modern technologies are quite fast in terms of their ability to implement memories and logic gates and things like that. And then here's the information that we have about the write signal. So at the rising edge of the clock, we have both setup and hold time. So we have to have a dynamic discipline associated with the writing into the register file. And we have a write address and write data that we have to supply along with an enable signal. And if the enable signal is high, this data, it will be written into the register whose number is given by the write address at the rising edge of the clock. And we have the usual, it has to be stable for a nanosecond or two before the rising clock edge and a small amount of time after the rising clock edge. And of course, the setup and hold time numbers vary depending on how much money you're spending on your memory and what technology is implemented. A question that comes up that you will probably ask yourselves is, what happens if I have an instruction that looks like this? Say I want to do an add C of R1, I want to add 42 to that, and I want to write it back into R1. Is there a problem if the write address, which is coming from the RC field, so this is the write address, okay, is the same as the read address? And the answer is no. If you think a little bit about how this is working, we can, as soon as the read address is stable, we get the read information out, and that happens very near the beginning of a cycle. As soon as we get the instruction from the memory, we will have the appropriate read address from the right bits of the instruction field. Shortly after that, a couple nanoseconds or so, we'll get the read information, the register file information out of the register file. We have all cycle to run it through the ALU and add a constant to it. And then at the end of the cycle, we can write it back into some register. It could be the register we're reading out of. And there's no confusion because the write happens right at the rising edge of the clock. So at the beginning of the cycle, we're reading out the old information. And at the end of the cycle, we're writing back in the new information. And it's okay if it turns out to be the same location as before. Okay, so now we get to that sort of by way of introduction, sadly a little longer than one might like, but I think what we'll do now is we can actually start drawing the beta itself, which is sort of more interesting.